All right, welcome everyone to another special class, and this is the second part of the class that I began on electric cells and electrolysis. In this part, I'll be covering electrolysis, so please pay rapt attention and make sure that you flow along with me. Let's now have a deep dive into it. So here we go. Electric cells and electrolysis part 2. In this part, we are dealing with electrolysis. So electrolysis. And I'm going to quickly define what electrolysis is. This is the process whereby a liquid conducts electricity by the movement of positive and negative ions within the liquid while undergoing chemical, let me write that very well, while undergoing chemical changes. So take note of that. Electrolysis is the process whereby a liquid conducts electricity by movement of positive and negative ions within the liquid while undergoing chemical changes. Please take note of this definition. So let me scroll up and now talk about what is called electrolytes. Electrolyte is a liquid which allows electricity to pass through it. E.g., you have salt solutions, alkalis, and then you have alkalis and dilute acids. So those are electrolytes. Non-electrolytes. These are liquid. Okay, so I'm supposed to define this with these are. These are liquids. So this other one, these are liquids which do not allow electricity to pass through them. So these are liquids which do not allow electricity to pass through them. Such liquid include distilled water, alcohol, liquid paraffin, and sugar solution. Let's note something here. Metals and hydrogen are deposited at the cathode, while non-metals and oxygen are deposited at the anode. During electrolysis. So please take note of this statement. Metals and hydrogen are deposited at the cathode, while non-metals and oxygen are deposited at the anode during electrolysis. So the anode may dissolve in solution. So take note of that fact too. We also love to talk about the fact that electrolysis does not manufacture electric charges. So it is the splitting of compounds by electricity. For example, water decomposes into oxygen and hydrogen by electric current. So electrolysis begins or starts when the electric circuit is completed. And it ends abruptly when the electric circuit is broken. So please keep these points. These are just points you need to keep in mind. All these definitions are no important points. So just keep them in mind. So let's talk about another important concept now. Faraday's laws of electrolysis. There are two laws. So under this we're gonna have first law of Faraday's first law. Let's put it in full. Faraday's first law of electrolysis. That first law states that the mass of a substance liberated during, let me calm down, states that the mass of a substance liberated during the process of electrolysis is proportional to the quantity of electricity passed through the electrolyte. So we said the mass of substance liberated during the process of electrolysis is proportional to the quantity of electricity passed through it. So later on, after I state the second law, I'll write the formula that encompasses or tells the story of both the first law and the second law. Yeah, today's class doesn't have to be necessarily so long. You need to go and read most of these things you have been, taught, and you need to digest them, memorize them in some cases. So Faraday's second law states that the relative mass of a substance liberated during the process of electrolysis states that the relative mass of substance liberated during the process of electrolysis is proportional sorry, to the quantity sorry, is proportional to the, I think I've stated quantity of electricity in first law, proportional to the, this time around, electrochemical equivalent. So it says the relative mass of a substance diluted during the process of electrolysis is proportional to the electrochemical equivalent. So one of the formulas that covers both laws is that both laws are talking about mass. And the same mass is proportional to quantity of electricity, if I call that Q. But we know that also the mass is directly proportional to Z, which is electrochemical equivalent. Now if we write it together, we say mass is equal to ZQ, because Z is the constant of proportionality here. So we now have mass as ZIT, because Q is the charge is equal to I times T. So current times T. So M equal to ZIT is the main formula here. So please keep that in mind. You can be asked any question from it. And then the idea is that, we want to talk about what's the unit of Z, or how does Z work. We'll now say, make Z subject of formula. Z will now be M over IT. I know that the top is measured in, some people measure it in gram or kilogram, but for most times, in this case, we say mass is measured. Let's itemize what we have. Mass measured in gram. T measured in seconds. I is current measured in ampere. So the idea is, if we go back to this formula here, where we just made Z subject of formula from the previous one, we have gram over coulomb. Now Q is quantity of electricity, and Q is ampere times time. That's the unit, or coulomb. That ampere times time is coulomb. So down here, could have had either ampere times time or coulomb. So, but most popularly we say, okay, Z is measured in gram per coulomb. Per coulomb. So per coulomb. So keep that in mind. So that's just the unit. And this is not the first time we're doing something with respect to unit. Let's quickly talk about some important examples. The question says, what is meant? Number one, what is meant by the statement the electrochemical equivalent of copper is So what is meant by that? The statement, the electrochemical equivalent of copper is this per coulomb. So all you have to do with this is that you use the law to interpret it. Because now electrochemical equivalent is, first of all, you say Z is equal to mass per charge. So we can say the mass the mass of substance liberated, or it's not just substance now, since they have specified that it's copper. They say it means the mass of copper liberated in a process liberated, not just liberated, liberated per coulomb of electricity. Because here now they have said it is 0.00033 gram per coulomb. So that's like over 1 coulomb. So it means the mass of copper liberated per coulomb of electricity during electrolysis is 0.00033 gram. So this is the mass, and it is per coulomb of electricity. So that's the meaning of this. That's what it means. So that's how to, imply. So you can decide to get that formula. What is up? The mass down. This is together. IT is Q. So keep all those things in mind. Let's now go to the second example, or just something to consolidate your knowledge. A current of 3A maintained, 3 ampere rather, maintained for 50 minutes. Deposit 3.48 gram, 3.048 gram of zinc at the cathode. We are asked to determine the electrochemical equivalent of zinc. Always told you that the best approach to a question in physics is that you list out the parameters given. So solution, what are we given? We're given current of 3A. That's I equal to 3A. What are we given again? Maintain 50 minutes. Maintain for 50 minutes. Time is 50 minutes. But then we can multiply 50 by 60 to have it in seconds. 3,000 seconds. Then we have that it deposits this mass of zinc at the cathode. We are now asked to determine the electrochemical equivalent Z, so we have to find. So we know that, let's recall, M itself equal to what? ZIT. So what we are looking for is Z. So Z equal to M over IT. And M is 3.048 over 3 times 50 minutes, but this time we use seconds. I've established that before, times T. So the electrochemical equivalent, after you use your calculator, in this case, we establish what that is. 3.048 divided by, this is 9,000. So that gives me 0.0003386, or you can say 3.386 times 10 raised to the power minus 4. What is the unit? Gram per coulomb. Have it above. Always put your unit after every calculation. Don't ever make the mistake of leaving it out. Let's go to applications of electrolysis. Applications of electrolysis. In industry, electrolysis is used in number one, electroplating of metals. And what does that mean? This is the process. Let me call this number one, number figure one. This is the process used in coating cutlery and other articles with copper. Silver, chromium, nickel, or gold. You said, or other articles, or can be utensils or whatever. Other articles, we can say that other articles. The article, how do you do it? The article is placed. Oh, it's plated rather. It's plated so it can be used. So the article is plated so it can be used as the cathode and coating metal. The article is plated so it can be used as cathode, and then the coating metal serves as the anode. Let me just shift this instead of raising it. And then coating metal serves as the anode. The electrolyte in electroplating, for the picture we're painting, the electrolyte is a solution of a salt of the plating metal. For example, in silver plating, of spoons, the spoon itself, in silver plating of spoons, the spoon itself, the spoon itself is the cathode. While pure silver is the anode. And silver nitrate solution is the electrolyte. So catch your breath first. So let's describe that process of electrolysis using that silver nitrate, the electrolyte. So we'll say this is what happens. The silver nitrate dissociates. That's the electrolyte in solution into silver ion and nitrate ion. That is, you have AgNO will break into Ag plus and NO minus, Ag3NO then. Or but no, but that's still no, because the ionization is already 3. AgNO breaks into this, breaks into Ag plus NO3 minus. So the process is that when electricity is passed through the solution, the Ag silver ions move towards the cathode. Keep that in mind. Let's paint a picture of what we have. This is let's say this is a container, and then we have the spoon right here, which is made of the spoon. And that spoon, we were already told that the spoon itself will serve as the cathode. For example, in the silver plating of spoon, the spoon itself is the cathode right here. White pure silver is the anode, and silver nitrate is the electrolyte. So let's say we have this liquid, the liquid silver nitrate. This AgNO okay, yeah. Let me confirm that it is AgNO and not something else. So I want to make sure I'm giving you guys the right signs. It's AgNO3. I said it. One nitrate. So yeah, so it's AgNO3. So it's AgNO3, and so this place there's a 3 here, and this thing is AgNO3. So this is NO3 minus. So please correct that. Yeah, so that's why I was having AgNO3, silver nitrate. We have the spoon which serves as the cathode. Then we should have the other guy that is what did you say we're using to coat the spoon? Silver. So this guy has to be the silver. So the silver ion, let me see. So now you connect these two over a battery. And then this is the silver, which starts as what? The anode. When you connect them like that, electricity will move from the anode, move in that direction from the positive guy like that. And then we have exchange of ions. NO3 in this electrolyte will move like this. NO3 let me write it first. NO3 moves like this. Why? Ag moves towards this, the spoon. So once it moves towards the spoon like that, we can be able to coat the spoon. So that's why we say when electricity passes through the solution, the Ag ions move toward the cathode. That's what you see happening. And so we say where they are discharged, we move towards the cathode where they are discharged. And then the silver ions move towards the spoon, and the spoon becomes coated with metallic silver. So another thing to note is that in this case of silver nitrate, the nitrate ions, this is the NOs, they remain, let's say the NO3 minus is remain in solution. And they keep combining with silver. So that the electrolyte does not reduce in concentration. Does not reduce in concentration. Let's move to the other application in the industry. We talked about electroplating, and then Roman figure 2 will be the purification of metals. So how does this work for for the case of electrolysis? Purification of metals. And in the electrolysis, let's see, the electrolysis of copper sulfate using copper electrodes. Copper is deposited at the cathode, while at the same time the copper from the anode goes into solution. So the purification of metals has to do with electrolysis. So we are talking about specifically the purification of metals like copper. In the electrolysis of copper sulfate to be precise, using copper electrodes, copper is deposited at the cathode, while at the same time the copper from the anode goes into the solution. So let me just keep telling the story. In purification, so please, this is anode in case I didn't write it well. In purification of copper metal, the impure copper is made the anode, while the pure, you see that idea? The pure copper is made, take note of these things, the cathode. So in this purification process, the impure copper is made anode, while pure copper is made cathode. When current is passed, copper ions are dissolved from the anode and deposited at the cathode, leaving the impurities behind. Are you seeing that technique? So they leave the impurities behind. The pure copper now is used in manufacture of electric cables because of its low resistance. Take note of that. Now, the last application we'll deal with before we call it a day in this particular section is I will just explain it briefly, the electrolytic preparation of metals from compounds. So metals such as aluminum, sodium, and potassium. So, comma here, and potassium are prepared from their molten chloride or hydroxide. by the process of electrolysis. So here is where we'll call it a day, and I'll see you in the next class.